Hello guys, so I'm going to continue with applications integration here. Okay, now in the last video we saw that the summation of I plus 1 divided by n squared from I equals to 1 all the way to n the whole thing equals n plus 3 divided by 2n. Now, why am I showing about summation? We were talking about integration, which is the opposite operation of differentiation, and now I'm talking about summation. Why? Because you see, later we're going to see that integration equals the summation of the areas of small rectangles underneath a graph. So if you have a graph like this, I just want to get a little bit ahead of myself here to teach you guys why I'm talking about this stuff. So you have a graph that's kind of like this, okay? All right, now let's say that you want this area, okay? How can you calculate this? Well, you see, the problem with calculating, if it were a straight line, if this thing here were a straight line like this, okay, then the area would be the whole thing, right? It's going to be very easy. It's this height here times this width, and you're going to have this entire area here. So that's pretty easy. But when the graph is a curve, so things are just going to go up and more and more and more and more. So how do you do that? Well, you see, what we have is that we're going to make summations of rectangles, okay? So there's going to be a rectangle here, and this rectangle can be left endpoint, based on a left endpoint, or based on a right endpoint. We're going to see that later. So we're going to call this point A, and we're going to call this point B, okay? Now, the more rectangles you have, the more precise you're going to be, okay? What do I mean by that? Well, let's just say that I'm going to divide this whole area in two rectangles. So you see, I'm going to do like B minus A divided by 2. This is going to be the width of the rectangle. Now the height, let's put so it's going to be right here in the middle, okay? B minus A divided by 2. It's going to be kind of like here. So here we're going to have, you see, you got a rectangle here with a width, and then you have another rectangle over here with another width. Now, what is this going to be? Well, if it's the left end point of the rectangle is this one here, okay? Now, what is the value of the graph at this point? It's 0. So we're just going to have 0 here, okay? This is not going to count at all. And here, the left end point of this whole rectangle is this one, okay? So we're going to have a rectangle over here like this. So we can see that the way we're going to calculate this entire area is just by adding this area right here. Now, this is not very precise, okay? Now, you see what I'm going to do is, like, instead of having a rectangle like this, let's just do B minus A divided by 4, okay? So now we're going to have something like 1, 2 divided by 4. Okay, let's see if this works. I don't know if this is going to work. Here, okay, now you have here, and now you have here. Okay, now you have 4 rectangles, okay, and let's just consider the left end point now. So this one is 0, this one is over here. So there's going to be a rectangle. It's not going to be perfect, but I just want to do something like this. Here we're going to have a rectangle here, and here we're going to have a rectangle here. Okay, so this one over here is 0, so you don't count that. This one over here has this much. This one over here has this much. Okay, and this one over here has this much. All right. Okay, now you can see that it's a little bit more precise. All right, now let's say that we make enough rectangles, we make the number of these rectangles, we're going to make these rectangles infinitely small, and they're going to be, so the width of the rectangle is going to be infinitely small, and there's going to be an infinite number of rectangles, and you're going to add them all up. You're going to see, okay, that you're going to do this. It's going to be more and more precise as the number of rectangles go. I mean, these rectangles are so thin, they're infinitely thin, that they look like straight lines in here. Okay, so this is going to be, for example, a rectangle, even thinner than this. They're going to be infinitely thin. I'm just showing this to you guys so that you guys can see it, because they're going to be smaller than an atom. Okay, so you're going to have another rectangle here, and another one, and another one, and another one, and another one. And as you keep going, you can see that you're going to fill out with infinite precision, okay, this entire area right here. These are very thin and numerous rectangles. So that's the idea. That's why I'm doing the idea of summation here. Of course, we're not going to have to use summation always, okay? It's just because that's the way integration is taught by this book that I'm using as a guide. So that's the idea of integration. Okay, about the left endpoint and the right endpoint, let's see if I can erase all this stuff in here. No, I can't. So, okay, I'm just gonna erase the whole thing. The idea of the left endpoint and right endpoint, let me show you. I'm gonna make two things in here, okay? And now I'm gonna make a graph like this. And I'll make a graph like this, okay? So the idea of the left endpoint and the right endpoint, I'm gonna put here, and I'm gonna put here. Okay, so let's just say that the width of the rectangle is b minus a divided by 2. I'm just gonna make two rectangles. This is a, this is b, this is a, this is b, okay? b minus a divided by 2 is actually a and b are the values of x. So we're going to divide this by half, which is going to be kind of like here, okay? Now here we go. In this example here, if we're going to consider the left endpoint, now what is the left endpoint of this rectangle here, of this width? Okay, it's going to be this part. And this part, what's the value of the graph in here? It's 0, so it's 0. Over here, we're going to use the left endpoint of this rectangle. What is the left endpoint of this rectangle? This one, okay? So this is the thing that's going to be used. So you can see that when you use the left endpoint, you're actually going to have rectangles underneath the graph. If I make, let's just make another 2 here. So we're going to make one more here. And I'm going to make another rectangle here, okay? Now, we're going to use the left endpoint of this rectangle, which is 0. Now we're going to use here. Now we're going to use here. And now we're going to use here. You see that all these rectangles in here, okay, all these rectangles, they're underneath the graph. Now you can also do over the graph. Look at that. I'm going to divide this by 2, so it's going to be in here. And this one by 2, so it's going to be kind of in here. And this one by 2, so it's going to be kind of in here, okay? All right, now we want to use the right endpoint. So for the first rectangle here, which value of the graph we're going to use? We're going to use the one of the right endpoint. So it's not going to be here that we're going to look. We're going to look here, okay? So here's the first rectangle, which is going to be this whole thing, okay? And here we're going to use this right endpoint of this rectangle. So we're going to use this whole thing here, okay? And for this rectangle here, we're going to use the right endpoint. So it's this one here. So we're going to sum all these things, okay? There. And for this rectangle here, we're going to use the right endpoint, which is going to be here. So we're going to sum all these things in here. Okay, so you see, when you use the left endpoint, you're going to have rectangles that are underneath the graph. So the area is going to be less than the area of the graph itself. It'll approach the area of the graph from the left. Okay, let's just say that the true area of the graph is here, a sub t. Now, the left end point is going to be over here, left end point. It's going to be over here, okay? So the true area of the graph is going to be larger than the left end point, and it's going to be smaller than the right end point. Okay, so, but you see, as the number of rectangles increase, and as the widths of the rectangles go smaller and smaller and smaller, this thing is going to approach here, and this thing is going to approach here. So it doesn't matter if you use the left or the right end points. They'll all approach as they grow infinitely small, as the number of rectangles grows infinitely large, and as the widths of the rectangles shrink infinitely small. Both the left end point and the right end point techniques are going to reach the same limit, okay? And the limit is this one here. It's the true area underneath the graph, okay? As n goes to infinity, you see this n in here? Look at this part of the screen. This n in here is going to approach infinity, all right? And this is integration. This is integration. Of course, we're not going to be using the summation thing. Later, I'm going to show you guys a different formula, okay? But that's the idea of integration. It's the summation of these things, okay? So, yeah. So that's why I'm using summation here. Now that you guys have this idea, what's going to happen in this thing here as n grows to infinity? Okay, remember, I can separate this thing here and have n divided by 2n plus 3 divided by 2n. Now, as n grows to infinity, this n in here, you're going to cut with this one, and this thing here is going to go to 0. That's why we studied limit. Remember that I studied limit, for example, what's going to be the limit of 1 divided by x as x goes to infinity? This thing here is going to approach 0. It's the same idea here, okay? It's the same idea over here. That's why we study these things. What I'm trying to do is connect the points for you guys. Because I'm talking about differentiation, then integration, then I stop the whole thing, and we're talking about summation. What does one thing have to do with the other? So this is what it has to do. So the limit over here is going to be 1/2, okay? And I don't know if you guys remember about this limit thing. Remember the largest power of the numerator is 1 here, and the largest power of the denominator is 1. So what you're going to do as n approaches infinity is you're going to take the coefficients of the terms where the single term where n has the largest power in the numerator and in the denominator, and you're going to make a ratio between these, right? If the power of the numerator is the same as the denominator, in this case it's 1, so it's going to be 1 divided by 2, and you have 1/2 here. If it were, let's just say that it was n plus 3 divided by 2n squared. Now, because the denominator is squared and in here is just 1, this whole thing is going to approach 0. Remember that? If it were, for example, n plus 3 squared divided by 2n, now the largest power of the n in here is going to be 2, because you're going to have an n squared here, and here's just 1. So as n approaches infinity, this whole thing is going to approach infinity, okay? I don't know if you remember this stuff from what we were doing before. Okay. All right. Now let's see. I'm gonna show you guys here the stuff. This is proprietary picture. Okay, it's not mine, but I'm gonna put this stuff in here, and I'll get another one, and I'll paste on top and here. You see that? So you can see that this is the left end point and this is the right end point. So over here, you're coming here, okay, and you have this stuff over here. Okay, now which of the endpoints are you going to use? Since it's the left end point, you're going to use this height, you're not gonna use this height, okay? If you were the right endpoint over here, you were gonna use this height, and the whole thing here was gonna be the rectangle, and you're gonna have something exceeding here, an area. This area here was gonna exceed, okay? Which is what happens in here. You see, you have an exceeding area here, you have an exceeding area here, you have an exceeding area here. Now over here, what you have is a lack of area. So you got, I'm sorry. So you have a lack of area here, and a lack of area here, and a lack of area here. And then you go like, okay, but summing these things, there's gonna be a mistake, which is either an exceeding area or a lack of area. Yes, but I already showed you guys that as the width of these rectangles become infinitely small, and as the number of rectangles become infinitely large, infinite, you have to get used to this idea of infinite, okay? It's infinite. Everything approaches infinity, either small or approaches zero. The width of the rectangle is going to approach zero, smaller and smaller and smaller and smaller. It doesn't matter how small it is, it's going to get smaller to approach zero even more. And the number of rectangles is just going to grow larger and larger and larger, infinitely large. As these things happen, both the left endpoint and the right endpoint are going to reach the true area of the under the graph, the true area under the graph. Okay, that's the idea. There's something else too. Later, I'm not going to prove this to you guys, but it's pretty obvious. Okay, that is, you see. Right now, we're going to do some exercises where the width of the rectangle, which is delta x, is going to be. So you have this, right? And you have something here, and you have a here, and over here you have b. So the width of the rectangle is going to be b minus a, which is this spacing here, all right, divided by n. What is n? N is the number of rectangles. So you can see that every rectangle is going to have the same delta x, okay? But truly, in order for this technique to work, the rectangles don't have to have the same width, okay? What is that? It's called the module or modulus. I don't know how they call it. So let's just say that you have something like this, all right? And they do a double bar here. So you have a rectangle with a double bar, and you have this, and you have this, or maybe, yeah, you have something like this. What does this mean? Okay, it means that the width of the widest rectangle, so the width of the widest rectangle is reaching zero. Now, if the width of the widest rectangle is reaching zero, is getting infinitely small and it's reaching zero, the widths of the other rectangles that are even smaller, they're going to reach zero even more, okay? So you're going to have an infinitely large number of rectangles, and all of them are going to approach zero, even if they're not the same size, the same width. They don't have to have the same width. For example, one is this wide, okay? This wide right here. The other one is way wider. So the other one is this wide right here. Now, I'm making these things big so that you can visualize them. But pretend that this has the width of an electron, okay? Which is that negative particle of the atom. Let's just say that this is very small. This thing here is like 0.0000000000000000001 meter, and it's getting smaller and smaller and smaller. This is going for zero. Now, if this is going for zero, this one is going to go for zero even more because it's way smaller than that one. Okay, so that's the idea. Here we're going to work in these examples with rectangles that have all the same width, but they don't have to have all the same width. As long as the widest rectangle is reaching for zero, okay, for a width of 0, the other rectangles are also going to have to reach for a width of 0 because they're even smaller than the widest rectangle, okay? And that's what the symbol here means. Forget about this arrow, okay? It's just this thing here. Okay. Okay. Now I'm going to show you something here. So here you have that, okay? The function is x squared, all right? And it's going from 0 over here to 2 over here. So what is going to be delta x? Delta x is going to be 2 minus 0 divided by n, which is 2 divided by n, okay? Now, since this is the left-hand point, what is going to be the value? Well, the value of, because you see, for example, what's going to be the x coordinate of this thing here? Well, it's going to be, it's because I'm going to show you something here. Hold on. Okay, so you have this 2n, okay, times I minus 1. I is going to start with a 1, okay? Since this is the left end point, you want the first one to be 0. See that starting at 0 here? It's starting at 0, okay? So when I is 1, no, I'm sorry. When I is 1, okay, since you want the left-hand point, and the left-hand point is starting at 0, you want, hold on, you want, what is mi? I know it's very complicated. I'm trying to find the words to connect the points for you guys, connect the dots to make you understand. Mi is gonna be the value of xi. Because you see, the value of x1 is not going to be 1, and the value of x2 is not going to be 2, okay? The value of x1, which is this x right here, okay, in the left-hand point is going to be a multiple of delta x, okay? So it's going to be delta x, so it's 2 divided by n in this case, okay? Well, let me just say this. It's going to be delta x, but it's x1, right? Is it delta x times 1 or is it delta x times 0? Since it's the left-hand point, it's delta x times 0. Okay? And what is 0? It's I minus 1, because I in this case is 1. You see the x sub 1 here? That means that I in here equals 1. Okay, now let's do I equals 2. Now you're going to have an x sub 2, which is delta x times, since it's the left-hand point, is going to be I minus 1, which is 1. In here, you're going to have delta x. In here, you're going to have still I minus 1, but I in this case is 2. Okay, oh, I'm sorry. Hold on. In here, this is going to be equal to 0. Why? Because it's delta x times 0, okay? Now in here you're going to have also I times delta x times I minus 1, but this case I is worth 2, so 2 minus 1, 1 times delta x. This is in the left-hand point. This formula right here is going to be generic, okay? It's always this formula for the left-hand point. For the right-hand point, for the right-hand point, I'm going to do this here to get a little bit more organized. It's going to be 2 divided by n, which is delta x, but this time it's times I, not times I minus 1. Okay? What why are you multiplying? Maybe you guys already understood this, but I'm trying to emphasize. Okay, so you have a rectangle here, whatever, and then you have another rectangle here. I'm gonna make this a little bit further apart so that you guys can see where one ends and the other begins. And then you have another rectangle here, okay? And then you have another rectangle here. Okay, so what I'm trying to find out with this formula, what is MI? MI is the x coordinate over here and over here and over here and over here and over here. So you can see that it's always going to be a multiple of delta x. The question is, how many delta x's are you going to add? Okay, for I equal to 1, equal to 1, because I always starts at 1, okay? It's convention. For I equal to 1 in the left endpoint, do you want 1 times delta x? 1 times delta x is going to be here. But this is the right endpoint. That's not what I want. That's why you do I minus 1 for the left endpoint. If I is equal to 1, I want to start 1 minus 1, 0. So I want to start over here. Okay? When I equals 2, I want to start at 1, which is where? Over here. When I equals 3, I want to start at 2, which is what? Over here. Okay? Now, if we're talking about the right endpoint, which is this thing here, okay, then when I equals 1, what is this? This is I times delta x, right? So when I is equal to 1, I want the right endpoint, which is delta x times 1. It's this one. When I equals 2, I want the delta x times 2, which is this one. When I equals 3, I want the delta x times 3, which is this one. Okay, this is the right endpoint. So that's where these formulas come from. What formulas? This one and this one, okay? This. So just keep that in mind. I'm going to rewrite these formulas for you guys. So here we go. We have a function, okay, which is x squared. Function of x, which is x squared. And I want the area under the graph, right, by adding all those rectangles. And it's going to be from A, which is 0, all the way to B, which is 2. So what's going to be delta x? Delta x is 2 minus 0 divided by n. What is n? It's the number of rectangles, which is 2 divided by n. Now, I'm going to use the left endpoint formula. So we have 2 divided by n times I minus 1. All right? And so what is this thing here? This is going to be the value of x, okay? This equals mi, which is the value of x for a certain I. The value of x for I1, the value of x for I2, the value of x for I3, okay? Now, what is the formula? It's x squared. So we have to get this thing here and square it, okay? So the formula, I'm going to put it over here. So it's going to be 2 times I minus 1 divided by n squared. Hold on. Okay. Okay. This is going to be the value that we're going to use for x. Okay? Okay, but you see the story is not done yet. This thing here is going to be the value of, what did I say? I said that mi, guys, I'm not confused. I just don't want you to get confused, but this is so confusing. That's why I have a hard time putting this in your minds at first. This is going to be this mi is going to be the value of x for a certain I. Okay, because remember, when I equals 1, it's not going to be x equals 1. When I equals 2, it's not going to be x equals 2. It's not the way it works, right? We have to find multiples of delta x, and delta x in this case is 2 divided by n. Okay, so the function is x squared, okay? So this is the value of x for this I. Since it's squared, we have to square this formula. But what are we trying to do? We're trying to do the area of the rectangle, okay? So if you have something like this, I'm going to put a big rectangle here, just so you guys can see it, okay? So this is the rectangle, well, here, yeah, over here. And this is gonna be, well, yeah, this is the rectangle. And I just want to count this area up to here. So you have a rectangle here and you got another rectangle here. Okay, how do you find the area of the rectangle? You have to get the value of x. Since it's the left-hand point, this one is going to be 0, okay? And this one is going to be this value. All right. Now, what is this x in here? The value of this x is the value of mi, okay? So, since it's this value here squared, we're squaring it. But what do you have? You're just going to have this stuff in here, okay? Here you got a certain value of x. This value of y in here, this height, okay, this height in here is actually going to be x squared because this function is f squared. Okay, here you got the x-axis, here you have the y-axis, y equals x squared. So for whatever this, what is the coordinate for this point? The coordinate for that point is going to be x squared, okay? So for whatever value of x is, the y is going to be x squared. Okay, this is the coordinate pair in the Cartesian plane. That's great. So I know, according to this value of x, I know the length of this stuff. What is the length of this stuff? X squared. That's great. But you still have to multiply by the width of the rectangle, because I want the area of the rectangle. I don't want just this thing here. I want the area of this rectangle here. So it's going to be this value times the width. Okay, so you have to multiply the width over here. And the width is what? 2 divided by n. So you got to multiply this by 2 divided by n. There you go. Now you have the complete formula. And this formula here, you want to find out what its limit is. Okay, it's going to be the limit of this formula as n approaches infinity. All right? I know it's very complicated, it's a pain in the butt, but that's what I'm trying to get to you guys. So this is the delta x. Mi is going to be the value of x for a certain index I. Okay? So for what's going to be x1 is going to be actually the value of m1, x1. Okay. What's going to be x2, the second value, is going to be equal to m2. Okay. Now what is m? Is a multiple of delta x. M equals delta x times something, times some kind of integer. Okay. 1, 2, 3, 4. Now what is it going to be? Well, that's what I'm saying. In the left-hand point, it's going to be I minus 1. In the right-hand point, it's just going to be I. Okay, so this is going to be the value of x for a certain index I. But once you have that value of x, you have to apply it in the formula here, which is squaring. That's why I'm squaring it here. Okay, and then you have to multiply to find the area of the rectangle. You have to multiply by the width of the rectangle. That's why I'm putting this 2 divided by n here. Okay. Okay, so let's try to develop this thing here. All right. This thing is going to be 2i minus 2 divided by n all right, and I'm squaring this and then multiplying 2 divided by n. So 2i minus 2 divided by n and multiplied by n. I just want to do this slowly. So this is going to be 4i squared minus 8i, right? Yeah, minus 8i plus 4 divided by n squared. And this whole thing is being multiplied by 2n. So you see what I'm going to do? I'm actually going to multiply already. So this n here is going to be n cubed. Okay? And this thing here is going to be, because multiplying by 2 is going to be 8, 16, and 8. So it'll be 8, 16, and 8. Okay. All right. Now, you see it's going to be the summation, right? I'm going to put a summation here. It's going to be a summation from I equals 1 all the way to n as n approaches infinity. Okay? Now, let's see. We've seen this before, okay? Let me think in here. You can, what is multiplying everything in here? You have 8, 16, and 8. You can factor out the 8, and you can factor out this n cubed, because you see, n does not depend on I. It's I that depends on n. N doesn't depend on I, so n is a constant. So we can get like n divided by n cubed out of the summation. We're factoring it out. Okay, so it's going to be I squared minus 2i plus 1. Okay? Yeah. So, and now what we can do is to actually separate this this summation in here. So I'm gonna put like, I don't know what the best way to do this is. Let me think in here. Okay. So let's do this in here. It's gonna be 8 divided by n cubed times, let's separate the summations, remember? So it's gonna be, and this whole thing, okay, every summation here is I equal to 1 all the way to n, okay? I'm just gonna put in this one. I'm not gonna keep repeating because I don't wanna clog the place, okay? I don't wanna clutter. So it's gonna be I squared here. The 2 is a constant, so you can get that out. So it's going to be minus 2, the summation of I, plus, it's going to be a constant, right? The summation of 1, of 1. Okay, now let's keep this going here. So it's going to be 8 divided by n cubed. And now, what is I squared? The summation of I squared from I, this whole thing here, okay? I is equal to 1 all the way to n. Here, I is equal to 1 all the way to n. Here, I is equal to 1 all the way to n. So, what is the summation of I squared? You guys remember that stuff? It's going to be n times n plus 1 times 2n plus 1 divided by 6. That's why we studied summation in the previous video, okay? And then you have minus 2 times what? I. and I is going to be n times n plus 1 divided by 2. And then you have the constant. The constant is just the constant times n. The constant is just 1, so this is going to be plus n. Let me see if... yeah, that's fine. It's going fine. I know, guys, it's crazy, it's big, it's boring. Okay. Now I'm gonna do this slowly. N cubed times. So holy cow, right? Holy cow. I'm gonna get this ready here, guys, because otherwise it's just gonna be too big. So it'll be 2n squared, okay? And then I have plus n in here, plus 2n is going to be plus 3n, 2n squared plus 3n plus 1. But since I'm multiplying it by n, this thing here is going to be 2n cubed plus 3n squared plus n divided by 6. Because I'm multiplying by this n, right? So I want to make sure that I'm not making any mistakes here. 2n squared, but it's going to be 2n cubed plus n plus 2n, 3n squared plus 1 plus n. Okay. All right. In here, you're going to have minus, okay? And then you have this thing here, which is 2n squared plus 2n plus 2n divided by 2. Yeah, divided. Okay, I'll do it in the next one. Plus n, and this thing here is actually multiplying everything. So I'm gonna do that. Okay. All right. Now let's see what we can do, right? Let's see what we can do in here. Here you're gonna have 8 divided by n cubed, and then you're multiplying. So is there anything n cubed in here? No, there isn't. So you have this 2n cubed. Oh yeah, you also have to, if you want to add these things in here, you want to have the same minimum common denominator, right? So I'm going to have to multiply this by, if I'm going to multiply this by 3, I got to multiply these by 3 too. So I'm going to have to put a 6 in here, 6 in here, and a 6 in here. And then I have to put a 6 in here divided by 6. All right. Now you see, let's do this slowly. 2n cubed, so it's alone, okay? 3n squared minus 6n squared is going to be minus 3n squared. Minus 3n squared. Okay. Now let's talk about the n. You have n in here, then you have minus 6n plus 6n. So the minus 6n plus 6n are canceling. You're just going to have plus an n here. Right? And this whole thing is being divided by 6. You don't have any independent terms in here, no 1s or 2s or blah, blah, blah. 6. Now we're going to simplify this stuff by 2, so it's going to be 3 in here, and this one here is going to be 4. Okay? And now look what we have. We have 4 thirds, right? Multiplying what do we have in, because the 3 I'm just putting it out, okay? Multiplying what? Let's see. The n cubed is multiplying everything here in the denominator, so I'm going to bring it inside and I'm going to separate the stuff, right? So you have 2n cubed divided by n cubed. And then you have minus 3n squared divided by n cubed plus n divided by n cubed. All right? Now look at that. As n approaches infinity, this thing will go to 0. This thing will go to 0. Why? What? Okay, I swear, this is the only exercise this size that I'm going to do, okay? I'm not going to do this anymore. For example, I could also prove to you guys that if you use the right endpoint, instead of using look at here. I know this screen is a mess, look at that. Okay, but look at this point of the screen here. Instead of using I minus 1, you can just use I, and I can prove to you guys that it goes to the same place, but I'm not going to do that. I'm just going to show you the exercise ready from the book. So n divided by n cubed, as n goes to infinity, because the denominator has a larger power than the numerator, this goes to 0. And here you have the same thing. You have squared on top and cube at the bottom, so this will go to 0. Now here you have cube and cube, so this one is cancelled with this one. And look at what you have. 4 times 2 divided by 3, so 8/3. All right, so 8/3 is actually the area under the graph. What graph? This graph right here. Okay, let me just erase this stuff. If you have a graph like this, okay, and you have here's x, this is the function x squared, and you're going from 0 all the way to blah, 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 blah. Now this is x equals 0, and this one in here is x equals 2. This area under the graph is going to be equal to 8/3. Now, look, later I'm going to show you guys that integration is the same thing as the summation. Now look at that. If you have f of x equals x squared, look at this. What is the integral of this with respect to x? It's x cubed divided by 3. That goes from 2 to 0. So what you do is that you substitute 2 in here and then you minus 0. So it's going to be 2 cubed divided by 3 minus 0 cubed divided by 3. Well, 0 cubed divided by 3 is just 0. 2 cubed divided by 3 is 8/3. See? Integration makes this whole process over there that I just showed you obsolete. Okay, so that's good. And I'm going to prove to you guys why integration is the same thing later. Okay, right now I just want to erase this mess. Because it was messy, I'm going to give you guys a break here and just copy these things. I'm going to paste them in here. Right, let me see if this will work. It works. Look at that. This is the exercise ready. Because the letter is more beautiful here, right? The handwriting, because it's typed instead of my ugly handwriting. So you guys can just take a screenshot over there and see. The lower sum that it says right here is actually the left endpoints. Okay. And now I'm gonna give you guys a treat. If you were the right endpoint, it will be the same. The same results. Okay. I'm gonna put the right end. Okay. Pause the video. Hold on. This is a mess. This is the left endpoint. This is the right endpoint. Now you can compare them side by side, okay? And you can see that in the end, the whole thing goes to the same limit, 8/3. You got 8/3 in here, and then you have 8/3 on the other side. Look at that. It's the same stuff, right? Guys, I think, let me see here if I, yeah, you can also see this. This is something that the book does, right? Look. Okay. This one in here is the lower sum, which is the left endpoint, and this one over here is the higher sum, which is the right endpoint. You can see that in the end, you got 8/3 in here, and you have 8/3 in here is the same. I don't know if I make another exercise. I think I will, because now I'm not going to explain so much. Yeah, I'm going to do another exercise just for fixation. I don't know what you call it, just to pound this content in your minds. So we got another function here. This time I'm not going to be so boring, okay? I'm just going to do things and hold on. Okay. I just want to see one thing here. That's weird. Oh, okay. All right. I thought that I had something here, but I didn't. Okay, so you have this graph. Okay, you have this function here, and then the domain is going to be from 0 all the way to 1. Okay, so what's going to be delta x? Delta x is going to be 1 divided by n, because it's 1 minus 0 divided by n. All right, we're going to use the right endpoint, so mi, which is the value of x for that certain I, is going to be I times delta x, right? Which is times 1 divided by n. So it's going to be this. This is going to be mi. So what do we have to do? We have to get the limit of what? As n approaches infinity of mi is the value of x for a certain I, so we got to cube this. So it's going to be I divided by n cubed times delta x. Delta x is 1 divided by n. All right, as n approaches infinity. Okay. So what do you have in here? You have I cubed divided by n squared. You want to do the summation of this from I is equal to 1 all the way to n, okay? Which is the same thing as 1 divided by n squared, the summation of I equals to 1 all the way to n of I cubed. I cubed, we saw that this equals 1 divided by n squared. I think I'm right. N squared times n plus 1 squared divided by 4. That's the value of the summation. You can see why I cubed, the summation of I cubed from I is equal to 1 all the way to n is n squared times n plus 1 squared divided by 4 in the previous video when we did the summations. So this is going to be equal to 1 divided by n squared, and then you have an n squared here which is just, you see this n squared here is just going to cancel with this one, so forget about this. So you have n squared plus 2, and hold on. Oh no, it's n cubed. I'm sorry. It's this thing, right? So it's I cubed times n squared. Yeah, it's gonna be n cubed times n to the 4th. This is gonna be 4 here. I'm gonna erase and do it again. I knew there was something wrong. This is 4, and this is 4. So what you actually have is 1 divided by n to the 4th, which was this thing here, times n squared, right? Times n plus 1 squared divided by 4. So this, I'm gonna make this thing disappear. I'm gonna transform this one into a 2. And now you have 1 divided by n squared of n squared plus 2n plus 1 divided by 4. Okay. I think you guys probably went deaf right now. Man, what a class. Okay, so this 1/4, I'm gonna switch these two, okay? So it's gonna be 1/4 times what? N squared divided by n squared plus 2n divided by n squared plus 1 divided by n squared. As n approaches infinity, this will go to 0, this will go to 0, this will go to 1, and what do you have? 1/4. Now, is this true? I mean, does this match the answer that we were going to get if we use the integration? What's the formula? The formula is x cubed, right? So if we're going to integrate that, it will be x to the 4th divided by 4. And from 0 to 1, you're going to do 1 to the 4th divided by 4 minus 0 to the 4th divided by 4. This is 0. And what do you have? 1 to the 4th is 1 divided by 4, 1/4. So 1/4. Look, you got 1/4 in here, and you got 1/4 in here. Okay. See here, guys, okay, so yeah, that's it for this video, and on the next video I'm gonna show you guys why the integration provides the same summation formula, okay, the same results as the summation formula provides, because then we're not gonna have to use all these things are gonna be much faster. Okay, see you guys on the next video.